Hi, this is Curtis. I'm majoring in physics. We are part of the NSF SEIGERT Purdue program here at the University of Delaware at the Institute of Energy Conversion.
Hello, my name is Nuha and I am an electrical engineering major.
Hi, I'm Bobby and I'm a chemical engineering major.
Today, I would like to talk to you about the Mobile Solar Experimental System, or MSES. This consists of 4 photovoltaic panels on a cart, and as you can see, it's mobile. This was designed by 2 UD alumni named Eric and Corey, who are former members of SEIGERT. It is designed for educational purposes and is used in K through 12 curricula across the country. So today we would like to show you the components of the solar cart as well as to give a demonstration as to how it works.
The Mobile Solar Experimental Station is a complete photovoltaic system, including electricity storage and handling components. It has 2 multi-crystalline silicon modules and 2 single-crystal silicon modules. The modules can be arranged using any combination of series and parallel connections. Also, the modules can be tilted to give the optimal angle towards the sun. Electricity produced by the modules is stored in 4 lead-acid batteries mounted on the bottom of the cart. These batteries are very similar to the ones found in your car. Batteries allow us to continue to draw electricity even if clouds shade the sun. Shown here are the components for handling electricity. The 2 black boxes on the bottom are charge controllers, and the yellow boxes on top are power inverters. Charge controllers act as the traffic controller for the system. They regulate how much electricity can be added to the battery and how much can be taken out. They prevent overcharging and deep discharge of the batteries, which can be detrimental to the battery life. The power inverters convert DC power, like what you get from a battery, into AC power, which is what you get from an electrical socket. Most devices that can be plugged into your wall at home can be plugged directly into the inverter socket. The smaller inverter on the left produces a modified sine wave, which is lower quality electricity than the pure sine wave produced by the inverter on the right. These components can be configured in any combination using connectors mounted on the cart.
I would like to talk about our most recent application of the solar cart. We have used it to provide hands-on PV education for students taking solar energy technology and applications class offered here at the ISC in the spring. This class consisted of both graduate and undergraduate students from different backgrounds. They worked on 3 different labs that reinforced solar energy concepts covered in class. One of the labs that they did was to get familiar with basic solar cell parameters that influence the performance of a solar cell, such as the short circuit current and the open circuit voltage, which are the current and voltage produced by a solar cell with no external load in the circuit. So one of the applications they used was by making the right or the necessary connections on the port, on the cart. Like here I'm using PV4, this 4th panel, and by connecting it to a multimeter set on a current setting, they could tilt the panel towards the sun and see where the maximum area is exposed to sunlight by recording the highest current recorded. Similarly, by changing the setting to voltage, they record the highest voltage. And by comparing these 2 values to the module specifications given on the back of the modules, they could note the difference between actual measurements and measurements taken under standard test conditions. And this is one of the concepts covered in class. Now I would like to introduce my colleague Lei, who would be talking about the effect of shading on solar cells.
Hi, my name is Lei Chen. I'm studying at the University of Delaware here at IEC. I'm under the contract from Arizona State University Quest program. Today, I'm going to introduce the effect of shading on solar module. So as you can see, here we have a module at a constant angle facing the sun, and also we have a multimeter connected to the module over here, and you can see on the screen that it's reading almost constant current from the module that generates. So now what I'm going to do is I'm going to use a piece of board to shade the module like this. And when I shade the module, and you can see the current output from the module has been dramatically reduced, although I didn't shade the whole area of the module. That is because all the individual cells inside the module are connected in series. So if one of them or a couple of them were not outputting current, then the whole module cannot generate any current. So that's the effect of shading. Next, I'm going to introduce my colleague Robert to talk about the effect of temperature.
Hello, my name is Robert Levelet, and I am another graduate student here at IEC and part of the Quest program. I'm going to be discussing the effect of temperature on solar cells. A lot of people in the solar course here at IEC were actually surprised to find out that solar cells perform best with a lot of sunlight in cold weather. I'm going to demonstrate here that this is because of the effect of temperature on the open circuit voltage. So I have here a cup of ice water and a solar panel here. We're not using the solar cart in this case because we don't want to damage any of the electronics. And you can see right now that the open circuit voltage is about 18.75 volts. Now, after I pour some of the ice cold water on there, we see that it increases. It's now reached almost 19.7 volts, showing a performance increase of about 1 volt. Now I'd like to introduce my colleague Bobby, who's going to talk about some of the other applications of the solar cart.
So one of our final exercises, we demonstrate how we use the entire PV system, including the batteries and power inverter. So we've been charging the batteries from the solar panel all day, and now we want to get some useful electricity using the power inverters. And we've actually been running one of the cameras this entire time off of that power inverter. So I have 2 lamps, an LED and an incandescent lamp, and I'm going to demonstrate both. So we want to compare the amount of power that we're drawing from each. So I have a kilowatt meter, which will plug directly into the inverter, and this will tell us how much power we're drawing from each. So first, let's try the LED lamp. As you can see, we've turned it on and we're drawing power from it. Now let's compare how much power we're drawing using the incandescent lamp. As you can see, it will turn on as well, and we're drawing a bit more power now. Now both of these inverters are rated to only 300 watts, so they'll run small appliances like lights or a fan, but they won't work for larger things. So we'll have Curtis demonstrate a couple of things that you won't be able to run off the system.
Since the inverter is limited to 300 watts here, we don't want to use any appliances that are going to be above that rating. Appliances would include a toaster, a coffee maker, and a deep fryer. If we tried to plug any of these in, the inverter would simply shut off.
This will bring us to the end of our demonstration here of the solar cart at the IEC. If you would like to find any more information about this solar cart, please feel free to contact illuminatedlearning.com. Thank you very much for your time.
just wanted to be. Okay, so. Yeah. What's your name? Katie. Okay.